my name is Caroline Hughes, and first and foremost, I would like to thank Martha, Tom, and the WinDC team for inviting me to speak to you all today. My background is not in economics, but in nuclear engineering. I came to the National Renewable Energy Lab a little over a year ago because I really just want to solve challenging and interesting problems. So working with the WinDC dataset really is the dream. I sincerely appreciate Maxwell Brown for bringing me onto this project to handle data management and processing. We as a team are extremely grateful for the entire WinDC team, particularly Tom, Adam, Andrew, and Goche. Your work on the WinDC dataset laid the groundwork for our project, and SLiDE would not be possible without it. So the National Renewable Energy Lab has a myriad of energy modeling tools, including the Regional Energy Deployment System, or REDS, and Tempo. However, none of these tools consider the economic implications of energy decisions. With our work, we seek to remove the overly simplistic and static assumptions concerning economic boundary conditions by developing a model of the economy and coupling that model with the detailed engineering-focused energy system models. To maintain compatibility with other NREL models, we've developed our model using the Julia programming language. This will expand the user base of the blueNOTE dataset to Julia-focused developers. So now I'd like to get into SLiDE, which is our acronym for the Scalable Linked Dynamic Equilibrium Model. And our goal is to use blueNOTE to build an open source CGE model for scalable integrated infrastructure planning framework in Julia. So you might recognize the slide from Max's presentation at the WinDC seminar recently. And I would like to use this to get into what is SLiDE. So it will be scalable in both region and sectoral resolution. It will be linked with other NREL models in the SIP framework, similar to the US REP READS linkage. It will also be dynamic, either recursive or intertemporal. This is built into the model at this time, though we're still working on recursive dynamics. And finally, this is a computable general equilibrium, or CGE model. So SIP, or the Scalable Integrated Infrastructure Planning Framework, is an NREL initiative housed under the Scientific Computing and Energy Analysis Directorate to unify models under one umbrella. So NREL has a bunch of different models that were developed by data scientists like myself and modelers like Max. And we want to bring all of these models together to really leverage all of our capabilities and make the best informed decisions that we can. So SIP is built using a programming language called Julia. And I'd first like to start with the challenges that we, as any Julia developer, have encountered during this project. First, there's a learning curve. It's challenging to learn Julia since there's very little documentation or resources to learn the language, although this is much better as compared to when I first started learning Julia several years ago. The language is under rapid development and their capabilities lacking, and sometimes capabilities will be added or even removed with frequent software updates. There have been 2 updates since we started our project, and I know I dread installing every one. This was an issue addressed on the Julia Slack channel, which I highly recommend to anyone interested in Julia development. When talking about backwards compatibility, they invoked the XKCD comic, saying that any update is going to break something for some users, so maybe we don't need to worry about them. This is I thought, a funny example where an update broke the workflow, where they took advantage of the CPU overheating to reach the control key. Another disadvantage of Julia is compared with GAMS is there's no MPSGE capability yet, although there could be in the future. But this means that the syntax is not as clean as GAMS, so it doesn't look quite as nice. Despite these challenges, Julia does have its benefits. Our model is going to be compatible with the SIP framework, and we're already leveraging some SIP capabilities. And using Julia really helps with speed when communicating between the models. Of course, a solver is a solver is a solver is a solver. So it shouldn't be too much of a benefit then, but it'll really be a benefit when communicating with reads and tempo and other NREL models. Julia also has some really cool functionality, such as different methods and structs. And I'll really get into that later and how we can use those to make for some really clean data processing. It is also just nice to have one language that can handle both the data processing and modeling. So you'll recognize this image from the WinDC website, and this was just a really great representation of everything that has to happen to the data before it can be used in the model. So we get all of this input data that y'all have aggregated, which has been incredibly helpful, and we have to parse it and make it usable in the model. So SLiDE has really taken advantage of a lot of Julia capabilities to parse, join, and scrub the data in one step. We start with YAML files written from Excel files, and we'll get into what a YAML file looks like and why this is so advantageous. But by executing these data operations defined in YAML files, we can have some really clean code that's easy to update and also easier to bring new users into Julia. So here we have an example of YAML defined data operations, where let's see if we want to rename columns, for example, it's just really clean from and to. And this is uniform across all different types of files that we could want to rename. And for each output file, has its own YAML file with a set of operations defined. And these are read into Julia as a dictionary that describes all these different operations. And then with one function called edit with, SLiDE can apply all of these operations to a data frame that stores the data and output something that's really nice. And by defining this so simply with a YAML file, it makes it easier for someone to get their feet wet with SLiDE without really being up to speed in Julia. So it gets rid of that barrier for entry to using SLiDE. However, since there are so many different output files, even just having one clean YAML file for every set of operations got to be a bit much. So we've created a spreadsheet that summarizes all of these data operations. This is really nice because we can look across to see what operations are being performed on different sets of data. So here we can look at the output columns, for example, which are ordered year, region, NAICS code, units, value. And we can see that that's uniform across these files. So we're going to go through an example now of really how this works and why SLiDE is so powerful in performing these simply defined data operations. And we're going to look at the agricultural data as an example. So if we read in this data, we'll see this data frame here. And there's a lot of superfluous information that really isn't necessary and is actually detrimental to the model, since this is just a lot of junk to carry around in memory. So I'm going to display here the chunk of code from the YAML file, and above it, the edits that are happening to that data frame as we go through this slide. So first we can simply read the data given an input path and the CSV file name where this is stored. And there are different data types that can define whether this is an XLS file or a CSV, etc. So this is really flexible for different kinds of data. There's even an input that can handle GAMs, sets, and maps. So we can read those in as CSVs. Since CSVs are much more friendly to Julia handling. So after we read in this data, you'll see a lot of extra information in these columns. And we can get rid of this using a data type that we've defined especially for SLiDE called drop. And this will drop all of the information in the specified columns. So we don't have to carry around this extra information. And here you'll see it defined in the YAML file. This is the Julia dictionary element that corresponds with an array of all of the drop operations to perform. So we can do this operation for any type of edit that we would want to make with just this line of code here. And after we perform the drop, our data will look like this. So already this is a lot nicer. And next we can follow a similar procedure to rename the data, and we've chosen column headers to be consistent with the set names in the WinDC build stream. So here we can take all of these, and again, with just this line of code, rename these columns. So finally, it's really nice to extract all of this information about the NAICS classifications parentheses, since this is just extra information. This isn't helpful to have here, and we really can't work with this in parentheses, so we can use the match data type to match on a regular expression and take what's in those parentheses and just save that in this column name. So after we perform the match operation, again, just with this line of code, this is what our data looks like. Next, we can use the add feature to add the units that describe what any additional information that we want to add to our data set. And here we're describing what type of units are the values. Again, this line of code. So now this is a bit more complicated. We can map from a parsing map to standardize all of these region names. Since these are different in every input data set, it's really nice to make sure these are uniform, and it's necessary to do so. So another thing we can do, and this is a change we've made in SLiDE as compared with the WinDC data stream, is we've done all of the unit conversions up front. So everything is converted to millions of dollars. So this is all just one YAML file. This is really in one fell swoop. We perform all of the data edits. So after mapping regions and units, we will get this output. And here you can see that we either do or don't need to add an extra column from the mapping file describing what's going on or bringing in that extra information. So before we can do any of that mapping, we need to get rid of this extra value, or D. I'm not really sure what that means in the original data, but we're going to make it a 0. So using the replace data type, we can replace this value with a 0. So finally, since all of these values can be converted to a number, we can perform an operation. This is another SLiDE data type. By multiplying all of the values by a factor to convert from dollars to millions of dollars. And then we can use the from and to fields to describe any other replacements that we want to happen. So here we'll replace units of dollars with millions of dollars just to be consistent. So after we perform that, here are our two new columns, and SLiDE saves that other information that was relevant to the operation. So we can keep track of what happened just by looking at what's going on at the end. But we really don't need that extra information when we finally save this data. So we can finally reorder the columns and convert them to their correct type. So you can see here is our final output column, and it looks much nicer than the original input. And this was all just done with the data operations defined in this YAML file. So something that's really nice about this is that, say, the National Agricultural Statistics Service decides to update this data set and we want to change one of these data operations, all we need to do is edit that YAML file that defines these operations and run SLiDE, and it will perform those data operations that we've updated. So there are a few different types of data operations that we did not go over. Those include grouping, different columns. So if something is just defined as consecutive data frames within one file, we can group those all with a column that describes them. And there are a few other data operations, and these are described in the Julia SLiDE documentation. So another change that we have made to the data stream and build stream process is defining all maps as CSV files. And this is really helpful from a programming standpoint, not to hard code anything, because if definitions get buried in code, I can get lost as a programmer with where everything is, where things are defined, and it can make it harder to update things. But if everything is just in one CSV file or it's like defining a global constant. So it just makes updates easier. So we have 3 different types of maps, and we've organized these by purpose. The first type that we got to in our example is a parsing map. And this can standardize data across files for compatibility. And this might come up with regions or units. Something we've added that's new to SLiDE is the unit conversion maps that are done during the data stream process, so we don't need to do those after the fact. And that really comes to defining everything in one place with those YAML files. So if we want to make a change, we know where to do it. Another type of map that is also new to SLiDE is a scaling map. And this is used to navigate between levels of the same type of data. And this can zoom out and zoom in on different regions. So an example of this would be for the core-based statistical areas. If we want to zoom in from state level data to county level, we can do that with these scaling maps. And I got this data just from the Census Bureau. And even recently, there is an update for, I believe, 2020 data. So I need to add that in. There's a final type of map which we've called a crosswalk, which navigates between different codes or identifiers that represent the same information. And this was surprisingly challenging for sectoral information because that incorporates codes from the BEA, NAICS, GSP, and SCTG. And these all map to some WinDC code. And this is something we've been talking about with folks on the WinDC team. And this is also something that comes up a lot if you check out the BEA website. They'll have FAQs like, do you have information on how to map these codes? And they kind of say, well, not really. So this was a challenge that we've addressed in SLiDE, just one map that will act as a crosswalk between all of these. So we approach this by doing a join on the NAICS and WinDC codes. And some of these were challenging to find, but what we needed were a translation from all of those codes on the previous slide to their NAICS counterparts. So I was able to find a reference where someone, I'm sure painstakingly went through and looked at which commodity names mapped for the SCTG and NAICS codes. So you're able to import this table into SLiDE and also leverage this tab in the BEA supply data that does relate the BEA industry codes to related 2012 NAICS codes. So perfect. Not really in the format we want. These ranges are particularly challenging to deal with, but we were able to use SLiDE capabilities to create these maps. And here, I'd like to zoom in on the forestry WinDC code to look at what this mapping information looks like when we perform this join, so we can really see what we're working with. And I think this suggests that there could be additional mapping that can describe how these are related, but having this table put together at least gives us a framework for how to do this and a basis for this information. Something that was really interesting is that there are only 2 rows of data that really mapped all the way across. And that was the forestry and logging and apparel manufacturing. So something else that we would like to address with SLiDE in the future is the regional scaling. Now we have the census data that can be used to scale up and down between these codes. And we can also, given a state, we can zoom out to look at, so we just want to look at New England as one group, we can do that. And currently in the source data that we have explicit data for the region for GSP and PCE, but we can easily sum over states given the mapping framework to zoom out. Now zooming in is more challenging, but we can do this in a method similar to how this is approached for the state disaggregation for the national model in the WinDC build stream. However, we do have explicit data for the county level for GSP data and for the core-based statistical areas for GSP and CFS. But otherwise, we can find that information again by disaggregating. Another huge benefit to incorporating SLiDE into the SIP framework is that we can replace some of the EIA data with different NREL models, such as reads, where we can see, and that's where SLiDE is really powerful in seeing how that linkage really affects the energy usage and necessities depending on the market. So we can either use the input data, or we can just replace this with information from reads and other SIP models. So finally, we are currently in the process of open sourcing SLiDE. So we're very excited to get this out to everyone within the next couple of weeks. We, as part of the code development process have been undergoing extensive code reviews to make sure we're really using Julia best practices. Since Max and I are both relatively new to Julia, it's really nice to just bring other programmers in and also lend their expertise to this project. There's also README information. Oh, I'm so sorry. Which we can auto-generate with the Julia Documenter package. And this is really helpful. So as we are developing, we can avoid some of those Julia traps of not having well-documented code by making sure that ours is well documented. So some other features that we would like to integrate into Julia are that regional scaling up or down. I'm personally very interested in the household disaggregation, possibly using tax return information, because I think that can really get it, give us insight into what different consumers need and look at the implications based on a socioeconomic level to see what impacts are on different communities. Another feature that we're working on is the model linkages, and we work closely with developers on those other SIP projects to make sure that our code is compatible with theirs and really get that working. So my presentation today has focused mainly on the data operations that produce the blueNOTE dataset for SLiDE. And I haven't mentioned the model side of things. So an update from Max is that we have replicated the benchmark via the canonical blueNOTE model and have added simple dynamics to that model, but we still have a long way to go. And some of the things that we would like to include are capital vintaging, the flexible functional forms, which are so easy to do in MPSGE, but these are pretty brutal in Julia Jump. Another focus of this work is to make sure that we really follow that theme of making things user-friendly and finding a good way to define these and data operations in ways that people who are not quite as familiar with Julia can get started. Again, we're interested in the household disaggregation and the model linkages. We are also interested in including international representation via GTAP or another data source, since right now this is really focused on US data. We're really excited about SLiDE and excited to bring more people into this project. We have an intern who started yesterday remotely for the summer and a postdoc starting in the fall. Since we're open sourcing so soon, we are very excited to include any of you in this discussion and in SLiDE development. I would really love to chat more about how to do this. So again, I would love to thank Martha and Tom for inviting me and all of the work that the WinDC team has done to lay the foundation for the work that we're doing now. I would also really like to thank Maxwell Brown for taking me onto this project as a non-economist. And we make a really great team as someone who is an outstanding economic modeler and me, someone who spends a lot of time on Slack Exchange. So I apologize, I'm a little early in ending, but I'm really excited to open this up to discussion. So thank you very much. Are there any questions?
Thank you, Caroline. Are there any questions or discussion points?
So I guess, Carolyn, thanks a lot for the talk. It was really interesting. Curious about, is YAML exist independently of Julia Jump, or is this a separate tool, or is this something that is routinely used by Julia programmers, or how does this is for this database operating?
Yeah, so I haven't seen YAML used in particular for database operations the same way we have, but YAML is used by a number of different programming languages. Python works with YAML. It is similar to JSON, so it's a nice way of, if you have a lot of variables you need to define, it's just a really nice way of doing that.
It looks like it's well documented and pretty clean.
Yeah.
The thing is, the one hurdle here is that you have to be kind of comfortable with writing regular expressions. That's the key.
Yeah, that is the challenge of that one particular function. And that's definitely the trickiest one to use.
And I guess so. The thing is that so YAML is this nice tool for managing data, but then at the modeling end, there's this challenge of how to represent functional forms. Can we do nonlinear equations, large systems of nonlinear equations in Julia Jump? I mean, the operations suggest that from a speed standpoint, once you get the thing written, it runs really fast. Julia's got a very good parser for automatic differentiation and so forth. But the challenge is how many months it takes to write the equations down, right? So that it's calendar time, not clock time, that the main challenge is.
Exactly.
So, that's something Max has been working on. You have been working, so you do mention here KLEM nesting. So I presume that that's writing down cost functions and demand functions and so forth. Is that started yet, or is this you guys still exploring with small examples?
Yeah, and yeah, Max has really been working more on the modeling standpoint and aspects of
What
that.
I found is, just to answer your question directly, what I found is that there's the complementarity package, which was written from somebody else, it's not native to Julia, can handle any sort of nonlinear functional forms, but the complementarity functionality within Julia, the native representation within Julia Jump, does not allow for any sort of exponential functions used in any of like zero profit or market clearing conditions, anything like that. So we're still sticking with this kind of homebrewed complementarity package until they update Julia to update Jump to allow for these exponent, any sort of exponent in these constraints. So
No exponents at this point in Julia.
there's just within the complementarity, features. So I could do it, but the constraint macro that's being used is only under the linear program representation, or I guess the QCP functions that are used to parse those into any sort of matrix that can be solvable.
Okay, I had heard that they had backed off on nonlinear equations, so that it's not come back yet. That was in an earlier version of Julia, right? And then
yeah, and this was the complementarity. Just like 2 weeks ago, they updated the documentation on their website to say, hey, we have these complementarity capabilities, but I've tried it. I tried converting, SLiDE over to the functions that they use or the macros that they use to create constraints, but it just throws up a bunch of errors that you can't have any sort of it's either squaring or square rooting of functions within those constraints. If you don't do anything if you do anything besides that, it just throws up a bunch of errors, and it's just not as functional as I'd want it to be. So I'm just waiting to see when they change that. For now, I'm using this kind of homebrewed package, which has the API to path built into it.
but who is generating the Jacobian though? Do you have to write your own Jacobian for this as well?
They have that homebrew package is doing the Jacobian translation of the constraints, and that's ugly because I can't, in GAMS I'll say something like, oh, equation zero profit condition for output or something like that, and I'll put the dollar symbol on that. But the problem is I can't do that in the Jacobian translation. I can't subset equations on those things, so I have to generate essentially square sets of constraints, and then fix the variables surrounding those. So it's kind of a hacky way to just, the model's much bigger, it still reaches the same conclusions with counterfactuals and those sorts of things, but what's being passed to path is a lot bigger than what would be under GAMS.
Are there any other people in the call who are using Julia Jump?
who I've been following is Oscar Dowson. I don't know if you're familiar with him. I just follow him on GitHub, but he's been working on that API to path.
I've been bugging Ferris to try to get him to like buy into this, but he doesn't trust that the Julia jump guys won't disable things. There's this backward compatibility problem, so he tends to be a little bit gun shy right now.
I don't blame him.
So,
This is Dominique from GTAB at Purdue. So it was really interesting, and I've been experimenting a little bit with myself. I'm a little bit skeptical, and I know Tom and I discussed last summer how we get, we can go down some rabbit holes with new software, and then in the end, we dump it. But let's wait and see. I mean, obviously, it has on the data handling side, it has quite a lot of nice new features. We're experimenting right now with R Markdown, which I guess is somewhat similar to Julia, in that it combines kind of built-in documentation with R code, and so you can kind of document what you're doing while you're doing it. I've been pretty impressed with it, but only doing it for kind of selected databases right now. But so just to give you an example, we're downloading directly the data from the World Bank using an API that has some R code around it. So we're bypassing totally the CSV part of it. We're just downloading directly from the World Bank servers, and then adjusting the data as need be in R. So I just wanted to know if you guys haven't been experimenting with that at all. The R Markdown, by the way, also uses the YAML specification.
yeah, thanks so much. I haven't looked at R Markdown, but that sounds really cool that you can also document what you're doing as you're doing it. And we've thought some about automatically downloading the data so we don't need to store it locally. And I get a couple of points with that. We would still have the same issues of needing to standardize all the data. So the SLiDE operations would still be extremely helpful. But one reason we are for right now not going with automatically downloading or accessing that online is that we want to be aware of when the data is updated, so there can be a real clear cutoff of we're maybe using this set of data. But that's something we've toyed with.
I'm still learning how to live in the virtual world, so I can't see anybody. I should actually open this up so I can see everyone's faces. I can't do that right anyway. I'm curious I understand the enthusiasm for moving to an open source modeling framework, and it's kind of a little bit frustrating because all the solvers are there. It's just a matter of getting the model converted over. I'm curious about whether or not it would make sense to do a simplified version of MPSG where you did the same thing that the current MPSG code does, is currently to the function evaluation to code that up in Julia. So you do the function and Jacobian evaluation all internally, and that way you avoid having to rely on their parser, on their handling of exponential functions and so forth. Would that be something that would be a strategy for doing this? I mean, I don't know. I'm just curious about how to move forward in this open source. If we're going to move in that direction, the question is, what's the best way to move? Because otherwise, you're at the whim of when they decide to bring in the functional forms that we need to have for the model.
I would personally absolutely love that. That would, yeah. I have spent countless hours racking my brain on, even just deriving simple functional forms, those sorts of things. But if we had MPSG and Julia Jump, I would be on cloud 9. Yeah, I'd be super happy about that. I think it's a useful adventure just because if we have the blueNOTE and WinDC data in there, it just gives another whole set of user bases for people that are just excited to use Julia Jump.
Yeah. The question is, do you have a programmer who's good enough to do this, right? I mean, it's Julia Jump programmers. These guys are in high demand now, so the cost is finding, yeah.
We have a few at NREL that at least could show me how to do it well. I would first look to Caroline just because, you know, she's a way better programmer than I am. So that's the first place I'd go, but then it'd be kind of, I'd reach out to a few different people that are really, you know, on the cutting edge of Julia Jump to get it done right. It's one thing that's on our to-do list. Sorry to cut you off, Caroline. It's one thing that's on our to-do list of just that KLEM nesting is, you know, I can work out the CES forms for each different sector and those sorts of things, but it's just a lot of work. It's a lot more work than if I were to just go into GAMS, put it into MPSG, it would take, you know, an afternoon or two.
Yeah, so another nice thing about Julia being open source is that if we do develop something that could mimic MPSGE, we could integrate that into Julia, like collaborating with that community.
The problem is you run into the same problem that you have with MPSG and GAMS. People don't like it because they want to see the equations, but the problem is writing down the equations is harder than actually just coding up the functional forms once carefully. So that's always, there's this tension there. It's really no different. The irony is this is the same as it's like 1987 all over again, right? Because in 1987 GAMS, it just was in the process of just come out with the PC version of GAMS. The function evaluator was good, but kind of a little bit flaky, and I couldn't get it to reliably do the CES functions well. So I just decided to code up a function evaluator myself and talk to the solver. And then I went, you know, so this was the same thing. It's exactly the same situation we had in 1987. Anyway.
What is that original function evaluator written in?
It's written in Fortran.
Okay.
It's very compact. It's very good code, but it's very tight, and so it's not. I don't think you can translate it verbatim. I don't think so. It runs very fast too. It actually is very good, but I think that you'd have to view this as a. I mean, there's all these indexing issues of how do you drive the functions. What, you know, there's all these things that you have to decide how you're going to handle it. But that would be. I think that. For a pilot, that might be the way to go, right? Would just be demonstrate the operability of this would be an interesting exercise. Just what, you know, do a simple version where you just handle Cobb-Douglas functions and you handle all the accounting for the income, and you basically do all the work that MPSG does right now, but do it for simple functions. Handle only Leontief for Cobb-Douglas, and then at that point see what it looks like, see if it works for. Because I think if you, and actually maybe even don't even do Leontief because you don't want to handle complementarity initially. If you worked initially with, I guess IPOpt is probably the most common solver. Just work on CNS, do a nonlinear equation version of the thing. We automate the generation of equations. That would be, you know, just demonstrate proof of concept would be.
If you're doing the NLP, you would explicitly write out the complementarity conditions too, correct? Would you? I guess
it's not really your equation system equation. Just say here is n equations, here n variables, solve it.
Okay.
The standard approach. This was Sherman Robinson's approach with earlier, the original Cameroon model. It's just you have a nonlinear system of equations and you have a vacuous objective function. You say solve, and whatever you optimize doesn't affect the solution because it's got no degrees of freedom. It's the standard sort of approach. So I think the complementarity linkages and getting all the equations mapped to variables, that adds a level of complexity that it doesn't really, for 99% of the modelers doing GE modeling don't really solve complementarity problems. They say they are, but it doesn't, the complementarity doesn't play a role.
I think I'm too accustomed now to just the complementarity representation that it'd be tough to go back to NLPs, but I think it's doable, absolutely.
Yeah, I mean, you need to have an association of variables and equations when you have a boundary that's going to be active. If it's going to hit, something's going to hit 0, then you have to know what gives way when it hits 0. But if all the variables remain positive, then it's essentially a nonlinear system of equations. You can still map equations to variables as a way of making sure you have the counting right, but you don't have to. Yeah, anyway. So maybe we should talk about that, Carolyn. It would be interesting sort of to exercise if there were interest in that. The question is how strongly you guys are wedded to going forward with Julia. If this is something that's high priority, then this is something I think might be better to take a baby step first.
Yeah, absolutely. I'm speaking for Caroline now too, because I prompted her for the question.
We're committed to Julia, so I think it's worth moving forward with that.
NREL too is getting rather committed. At least the Strategic Computing and Energy Analysis Center is very committed to it too.
In the broader numerical analysis community, there's a lot of momentum behind Julia. People have been really excited about that.
Yeah, the secret is just to first get a working example that illustrates a general. You just have a general set of functional forms, a general function that you're going to evaluate with Julia, and you're not going to rely on the automatic differentiation tool, but you're just going to write their own derivatives. You're just going to do it all yourself. That's for the function evaluation, and then get it to pass that to the solver. If you just demonstrate how to do that as the first point, then moving forward is not that difficult. I think rather than trying to jump into a big model initially, just keep it simple and generate an example of how that works. Yeah.
Anybody else?
Yes, this is Ron Sands from the Department of Agriculture. Thank you, Caroline, for your nice presentation, and thanks, Max. Also, this is really fascinating. I'm trying to build up the modeling capability within my research organization, the Economic Research Service at USDA. But I just wanted to answer a question that you raised, Caroline, in your presentation. What does the capital D in parentheses actually mean?
Thank you.
So I've been reviewing some ERS research reports and actually learned what that was. D stands for disclosure. It's a disclosure limitation where the sample gets to be too small, where you start to risk exposing numbers from individual operations, agricultural operations. And so at that point, the National Ag Statistics Service says you can't release those numbers. So that's where the dollar numbers in your table started to get small, which means you got a small number of operations. So I just wanted to clarify that. And thanks again for the nice presentation.
Thank you so much, Ron. Do you think replacing the D with a 0 is a fair approximation?
There are probably multiple better options that could have been used to indicate that, but that's what NAS uses. So.
Okay.
Sure.
Great, thank you.
Sure, you're welcome.
Anybody else?
Hey, this is Drew. Thanks for your presentation, guys. I was just curious on the regional scaling aspect of your routine that you've been talking about. So you noted that there's some gross product data for counties and CBSAs. Have you written the routine that actually that sort of disaggregates the WinDC data to those levels?
We have not yet.
Okay. Okay, cool. I was just curious.
I think that's somewhat reserved for next fiscal year, unless we get ahead of ourselves by the end of this fiscal year. But it looks like we'll have our hands full. So,
Yeah, no,
if you have any
sounds like
tips, I know you guys started down that road. So,
yeah, I think we got to the same point roughly as what you had talked about, and so far is just sort of acknowledging the relevance. But perhaps there's some sort of collaborations in the future then.
Absolutely.
Anybody else? Okay. Thanks, Ola. Thanks again, Caroline, for your interesting presentation.